Today we're going to talk about climate policy, and we're going to do so in 3 chapters. I'm going to start with what has been agreed in international law about what should be the targets for greenhouse gas emission reduction. Then I'm going to talk about cost-benefit analysis, how an economist would look at that. And then finally I'm going to talk about the co-benefits of climate policy and how that affects optimal climate policy. This is where we are in the sequence. First couple of weeks we talked about emissions, emission reduction, instruments for emission reduction, cost of emission reduction. Then we spent considerable time on the impacts of climate change, why we actually think this is a problem, and as well as some of the ramifications of that for climate policy. And then in this final block we're going to talk about optimal climate policy, what we should be doing about this problem. But as I said, I'm not going to start with the economics. I'm actually going to start with international law. We're going to have a look at Article 2 of the United Nations Framework Convention on Climate Change. We're going to look at the carbon cycle, which is not law but biology and physics, a bit of chemistry, and then we're going to talk briefly at Article 2 of the Paris Agreement. And then after that, cost-benefit analysis and the co-benefits. The United Nations Framework Convention on Climate Change was negotiated in 1992 in Rio de Janeiro. It has a bunch of articles. It is essentially a framework convention. It sets up rules for negotiation about international climate policy, but it also sets a particular goal, and that is done in Article 2. And Article 2 is reproduced here. The ultimate objective of the United Nations Framework Convention on Climate Change is to achieve stabilization of greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. Such a level should be achieved within a time frame sufficient to allow ecosystems to adapt naturally, to ensure that food production is not threatened, and to enable economic development to proceed in a sustainable manner. The UNFCCC was, as I said, negotiated in 1995. It entered into force was negotiated in 1992. It entered into force in 1995, which is very, very rapid for international diplomacy. And one of the reasons for that is that it is very difficult to disagree with its ultimate objective. And this treaty aims at preventing danger, or rather preventing dangerous human interference with the climate system. And preventing danger is something that everybody can easily get behind. Note that danger is not defined. It just says we should not do dangerous things. And that is, of course, something we can all agree on. It does seem to specify what is meant by dangerous anthropogenic interference, but it doesn't really. Just let us have a look at the language. So, such a level should be achieved within a time frame sufficient to allow ecosystems to adapt naturally. Again, it's very hard to object to this, but it's also very hard to agree on what this actually means, and that is, of course, what diplomacy is all about. If you have a whole bunch of countries that disagree on something, then it is the aim of diplomats, it's the job of diplomats to come up with language that everybody can get behind. And you may say, well, this actually imposes a fairly stringent target on greenhouse gas emissions, but it does not, because ecosystems, different definitions of that. What would be a sufficient time frame? Different ecologists, even if they agree on what is an ecosystem, would draw different conclusions about that. But the killer word there really is naturally. If we look, for instance, at the Younger Dryas event, where after the end of the last ice age, so This is a graph drawn by paleoclimatologists who work in the opposite direction in time than we do. So the further to the right is longer in the past. So you sort of like see us come out of the ice age, temperatures are rising, and then the temperature plummets, and then the temperature jumps up again, and then we go into a more stable regime, which we are now leaving, right? But this was, the younger dryas was a purely natural event. This was definitely not caused by greenhouse gases, was definitely not caused by burning of fossil fuels or anything related to humans. So this was a natural thing, and ecosystems made it through this. And if we say, well, ecosystems should be allowed to adapt naturally, then you could say temperature should not go down faster or not go up faster than at the beginning and the end of the younger dryas. So that doesn't really impose any constraint on greenhouse gases, not any meaningful constraint. The same is true for the third sentence, the third clause that you see that defines dangerous anthropogenic interference: to enable economic development to proceed in a sustainable manner. Well, we don't really know what sustainability means, or there's very different definitions of sustainability, the weak and strong definitions that we talked about last term. But also it is not clear whether we see climate change as a threat to economic development, or whether we see climate policy as a threat to economic development. And people who are very green would obviously say that climate change is a threat to economic development, and this therefore poses stringent conditions on future greenhouse gases. But you may also argue that climate policy poses a threat to economic development, and therefore this puts an upper limit to how ambitious climate policy may be. And the same is true for the second clause, to ensure that food production is not threatened. And again, it does not. It's a good thing that food production is not threatened. We all like to eat, but it doesn't specify the threat. Is climate change the threat to food production, or is climate policy the threat to food production? What you're looking at here is a graph from a study that comes out of the Pacific Northwest laboratories, national laboratories. There's the second in there. In the top, panel A, you're looking at global land and its allocation to various things, desert and unmanaged forest, pasture lands and crops, over this century, projected by a particular model in a particular scenario. And this is the case without climate policy. And then in panels B, C and D you see increasingly stringent climate policy. And what you see is that the light green essentially takes over, that a lot of land is devoted to growing biofuels. And this could be seen as a threat to natural systems. You definitely see unmanaged land go down, so this is a threat to natural ecosystems. But you also see, if you look closely, that cropland is going down, and the production of, or the use of lands that are perfectly suitable for agriculture and using them for biocrops, biofuels, actually puts a pressure on food prices. And this is a model projection, what we saw some 10 years ago at the so-called tortilla riots in Mexico. No country without maize is what the banner reads. And those tortilla riots were caused by a rise in the price of maize and therefore tortillas, which is a staple in Mexico. And there's good reason to assume that the price of maize was driven up by the bioethanol policies of the US, where by now some 25% of the maize crop is diverted to making of ethanol and therefore cannot be used for the making of tortillas, which drives up food prices in places like Mexico. So there's a real trade-off going on there. And therefore, if you read the second sentence of the United Nations Framework Convention on Climate Change, Article 2, you see that it's actually very easy to agree on this. It's very easy to say, yes, we should prevent danger, everybody agrees. But then the second set of clauses can be interpreted such that they serve a very conservative agenda, but also that they serve a very green agenda. And that partly explains why this particular treaty was so popular and was so rapidly adopted by basically every country on the planet. So you may think, well, this does not really set a target, but it does, because there is one word in Article 2 that meant something different than what the people who wrote it up thought, and that word is stabilization. And what does stabilization of greenhouse gas concentrations imply? Let's do a little bit of math. Let's assume that the concentration of greenhouse gases in the atmosphere is denoted by m, and that it's governed by a first order linear difference equation. That is, the concentration at time t depends on the concentration in time t minus 1 times some coefficient delta, which essentially is a retention factor. This is, if there's 100 tons in the atmosphere this year, then 99 tons will still be there next year. And then of course what we need to add as well are our emissions. So concentration in this year depends on the concentration in the previous year plus the emissions of last year. So this is a linear equation. It's a difference equation in the sense that m depends on m in the previous period, so that means it's a difference equation, and it only depends on its immediate past, and that gives you the word first order. So this is a first order linear difference equation. Now what does stabilization mean? Well, stabilization of concentrations mean that m doesn't change, or that mt is equal to mt minus 1. Or if you want to maintain stabilization forever, then essentially what you can do is drop the subscripts, and then we have the equation that m is delta m plus e, or m is e over 1 minus delta. So stabilization of stabilization of concentrations, m, means stabilization of emissions, e. The two are equivalent in this system, and if we can't agree on what is the appropriate level of m, then we also can't agree on what is the appropriate level of e. And we've actually learned nothing, right? And this may have been the thinking of the people who wrote up Article 2. But this representation of the carbon cycle is wrong. And that goes back to this particular graph, and you saw a variant of this in week 1. And I talked about the stocks of carbon in the ocean and in the deep ocean and in the terrestrial biosphere, and of course in fossil fuels. And what we're concerned about is the stock of CO2 in the atmosphere. I talked about all these stocks, and I talked about the fluxes, the annual emissions of CO2 by the burning of fossil fuels, which is of course the driver of our concerns about climate change, and how that is small compared to the gross fluxes of carbon exchange between, say, the terrestrial biosphere and the atmosphere, which measures around 120, whereas our emissions are only around 6. But then the big difference is, of course, that for all those natural emissions there is a counterbalancing natural uptake, whereas that is not the case for our burning of fossil fuels. and that implies the accumulation of CO2 in the atmosphere, and that drives the greenhouse effect and therefore climate change. Now, I talked about most of these things now 8 weeks ago or so, right? But I did not talk about this tiny little arrow that you see to your extreme left, 0.2 for weathering. And you may have thought, well, that is because it's such a small number, why would we talk about it? And it's true that it's a relatively small number, but it also tells you something about how the carbon cycle works. So this weathering is essentially a chemical reaction of rocks to stuff that is in the atmosphere, and certain types of stone interact with the air and gradually take out CO2 from the atmosphere, and as a result, because they take up an element, those rocks are growing. Now, rocks grow very, very, very slowly. This is essentially a geological process. And on a human timescale, rocks essentially stay the same size, but they do grow, albeit very slowly. And that is why that number 0.2 is so very small. Now, this may seem like an irrelevance, but it is not. In 1988, these two gentlemen, Ensmeyer Reimer and Klaus Hasselmann, discovered that, at least mathematically, we should not think of the atmospheric concentration of CO2 as the atmospheric concentration of CO2. Really, we should be thinking that there are 5 different atmospheric concentrations of CO2. And the thing that we measure, M, really is the sum of those 5 subcomponents, Mi. And each of those Mi's are governed by their own first order linear difference equation. That is what you see here, that MIT is delta I plus MIT minus 1 plus not the emissions in the previous year, but the share of emissions that is allocated to this particular, let's call it a box in the atmosphere, where of course the sum of those shares, alpha, should add up to 1. Now that's all very nice, and then they estimated those retention coefficients delta, and they found that the first delta has an atmospheric half-life of around half a year. No, yeah, that's no, sorry, that's around 2 years. It's a half-life of 2 years. So the way to think about this is that after 2 years, half of that CO2 is gone. Then after 4 years, 3/4 of that is gone. After 8 years, 87.5% is gone, and so on and so forth. That is how to think about it. And then the second characteristic half-life, delta 2, is 17 years, and then there's a component with 74 years, and then there's a component where CO2 disappears very, very slowly. Characteristic half-life of 363 years. And then finally there is this component of rock weathering, of geological processes that remove CO2. And that means that at a human time scale, this stuff doesn't disappear. It just stays in the atmosphere practically forever. And that component is at the moment around 13%. So 13% of the CO2 that we stick in the atmosphere stays there forever. The first component that I talked about, with a half-life of 2 years, that's about 20% or so. And 20% of the CO2 we stick in the atmosphere, half of that will be gone in 2 years' time, but 13% will stay in the atmosphere forever. Now, that poses a challenge to our stabilization equation, right? We said that the condition for stabilization is that mt is equal to mt minus 1, or m plus delta, m is delta m plus e, where the solution is m is e over 1 minus delta. But if delta is 1, then you're dividing by 0. So that doesn't work. So we have a problem there. But fortunately, there is another solution to the equation m is delta M plus E, for delta is 1. What that says is M is M plus E, and that implies that E must go to 0. This follows from the properties of the carbon cycle. There's very little we can do about this. Stabilization of the atmospheric concentration of carbon dioxide implies that emissions have to go to 0. Now, as I said, I don't think that the people who wrote up Article 2 of the UNFCCC realized that this is the case, and one of them I know pretty well, and I'm fairly sure that he didn't know this, but that is what was agreed in international law. Emissions have to go to 0. By now people are beginning, in political circles, are beginning to realize that that is the case, but for the first 20 years or so they called for a 50% emission reduction in the long run, or 80% or 90%. No, emissions have to go down by 100%. The Paris Agreement, 24 years after the Rio Agreement, puts more meaning to what is the appropriate level. We know that in the very long run emissions will have to go to 0. That has been agreed. That's the only way to stabilize climate. In the Paris Agreement they put more structure on this. They actually said the following, and again they did so in Article 2. This agreement aims to strengthen the global response to the threat of climate change by holding the increase in the global average temperature to well below 2 degrees above pre-industrial levels, and pursuing efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels. So that is the current international agreement, and of course not every country adheres to that. The United States, for instance, is likely to leave the Paris Agreement one day after the presidential elections as currently scheduled, but other countries have signed up to this, and this seems to be the international agreement. We're gonna miss this. This may be written down in something that resembles international law, and definitely is an international treaty, but we're not going to hit this target, and that can be seen from this particular graph and the text below it. We know how much CO2 we have emitted in the past. We know how much it's warmed. We know roughly how much more it will warm if we put more CO2 in the atmosphere. And that means that you can work backwards from any temperature target to how much CO2 is left for us to emit given that target. And if we want to limit global warming to 1.5 degrees Celsius, then depending on who you believe and depending on what sort of probability you want to attach to hitting this target, whether you want to hit it with 100% certainty, which is impossible, or with a 2/3 certainty, or maybe you only want to hit it with an even odds target, even odds of hitting it, then depending on how you configure this, we can emit roughly somewhere between 420 and 580 additional gigatons, billion tons of carbon dioxide. And if you want to be more lenient and you go to the upper range of the Paris target, then we will be allowed, or we can emit perhaps 1200, perhaps 1500 gigatons of CO2. So that is what Paris implies, but now if you look at the two graphs that you see, in what you're looking at there is the projected emissions from the current capital stock. So the very bottom one to your left is electricity. So essentially these are existing power plants. Some gas-fired, some coal-fired, a few oil-fired still. And they're in the year 2018, so this is the current stock of power plants. And we know the age of these things, and if you then take their standard lifetime, for coal-fired power plants it's 60 years, for gas-fired power plants it's 40 years. And some of these things are brand new, right? Some of these things were built last year in India and China and in other places. So if you let them run for their normal commercial lifetime, that means that the last one of these things will close by 2060, and that is what you see there. And you can then repeat the same trick for all sorts of machinery in industry and cars and trucks and boats and what have you. And the result is the graph that you see there. If we replace everything at the end of its natural lifetime, and at that time we replace it by something that is carbon free, then the area under the curves that you see there is the total emissions of CO2, and that amounts to some 850 gigatons, which is greater than the carbon budget for 1.5 degrees of warming, and it actually comes very close already to the carbon budget for 2 degrees of warming. So that is the figure on the left, and then the figure on the right, you're looking at the same picture, but now not by type of energy use, but by country. And then you immediately also see who carries most of the weight here, and that is actually China. Rest of the world and India are actually the biggest players there. And the implication of this is very simple, that we're going to miss the 1.5 degrees target unless we can convince the Chinese to prematurely close a large part of their power generating park. It's going to be extremely costly. But even that is not enough. What we also need to do is to make sure that as of 2018, which is by now 2 years ago, we should not build any new anything that runs on fossil fuels anymore, which is obviously not something we have done over the last 2 years, so the problem is slightly more severe than it was when these graphs were drawn up. And of course, it's nowhere on the horizon that we're going to do that. Take international transport, road transport for instance. We are now talking about having fossil fuel cars from 2030 onwards, and many people would say, oh, that's fairly optimistic, these cars are not quite ready. And this implies that unless you take large-scale capital destruction for granted, which I do not, we're gonna miss the Paris targets, and not by a little bit.